Now we begin the process of solving with duality. So we're going to start with the fundamental theorem of duality. So we call the original LPP the primal LPP, and then when we transpose, we call the other problem the dual problem. So the primal and the dual LPPs have the same optimal value, so they have the same P or the same C. If the primal is a C equals, then it has the same value as the dual for the P equals, but the solutions would be different. You noticed in the previous example with showing you the duals that one had variables x, y, z, the other one had variables u and v, but you'll notice that their values come up the same. Here's the steps. Represent the problem as a simple matrix. This is called the primal problem, kind of like the primary problem. So the simple matrix is putting the objective function at the bottom. That's very important. So if you want to do that first, you can. And these just kind of help us organize things. You don't have to put these bars in here. We go 1, 1, so the coefficients of the objective. And then if you want to leave that blank, you can, or you can put a 0 there. Same thing for the first constraint. We've got 1, 2, 2, 60. And for the third constraint, 2, 1, 3, 60. So this is the primal problem. Now we want to take the transpose of that matrix. So remember, if this is a 3 by 4, then the transpose becomes a 4 by 3 because the rows become the columns and vice versa. So 1, 2, 2, 60 is going to go down. And then 2, 1, 3, 60 is going to go down. And then 1, 1, 2, 0 is going to go down. This is referred to as the dual problem. Now when we write the dual problem, remember from the previous page we used different variables because it is a different problem. This one uses x, y, z. I'm going to use u and v here. So I'm going to write it down. We're going to have u instead of x plus 2v. Now if we were doing this one with the simplex method, we would be adding in slack variables. But here we're going to use our slack variables as the original variables. So we're going to introduce x as kind of the slack variable here. And this is equal to the constant of 1. We're going to do the same thing for the next equation. So 2u plus 1v plus, we're going to use y for the slack variable on this equation, is equal to 1. And then 2u plus 3v plus, we're going to use z on this third slack variable, is equal to 2. And then for my objective function, the dual is going to be a p equals, and it's going to be a maximize. So p is equal to 60u plus, so reading it off from here, 60v. So this is to maximize. And this would have been the constraint u plus 2v is less than or equal to 1 from the maximum. This would have been 2u plus v is less than or equal to 1, and this would have been 2u plus 3v is less than or equal to 2. So we added in those slack variables to turn the less than or equal to into equals. And we should probably, so let's go ahead and put that over here as well, 60u plus 60v. Let's go ahead and move this equation around so that it's in the right form. Remember, the p has to stay put. We want to move the other two terms to the other side, so minus 60u minus 60v plus p is equal to 0. Now we're going to solve the dual problem, because remember we turned it into a standard maximum, right? It had all less than equal to, and it was to maximize this equation here, this objective function. So the standard max is the dual problem. We can put our coefficients down. We've got 1 for u, 2 for v, 1 for slack variable x, nothing for slack variables y and z, nothing for p, and 1 for the constant. The next equation, we've got 2 for u, 1 for the coefficient on v, The slack variable x is not there, but we do have a slack variable of y, so we need a 1 there. 0, 0, and 1. Third equation, we've got 2, 3, 0, 0, 1. So reading off from here, no x, no y, but we do have a z, and that's equal to 2. And finally, we put that objective function in the proper order with everything on the same side as p. So we got negative 60, 0, 0, 0, 1, and 0. So right now, the active variables are the slack variables, the x, y, z, and then the p. But we're trying to solve the dual problem, so we need to solve for u and v. So we're going to use the simplex method, much like we did before. So right now we've got x, y, z, p. But we need u's and v's over here if it has an optimal solution. So let's go ahead and get this in our calculator. So this one is 4 rows by 7 columns. Don't forget to go back and double check your columns. Now you're ready to look at the comparison of the most negative numbers in this bottom section here, and you'll notice there's a tie. So when that happens, you just choose one, and it probably means that there's more than one optimal solution, but we only need one solution. So I'm just going to choose this one. And then we're going to do the test ratios. So I'm using these as my A's, and then I'm going to use column 1 as my B values. So 1 over 1, 1 over 2, and 2 over 2. So 1 over 2 is the smallest, which means I would choose that as my pivot. So second, quit. Call up your pivot program. Enter. Enter. All right, so we're going to pivot on row 2, column 1. And it looks like we've still got negatives in the bottom row, but I've only left room for the initial tableau and final tableau, so we can use that nice little shortcut method that I showed you previously. So notice where do we have negatives at? We only have negatives on that bottom row in column 2. So we're going to be looking at column 2 to choose our pivot. So let's go ahead and write down those A values there, 3 halves, 1 half, and 2. And then let's put our coefficients from the end. Or our constants from the end. So we've got 1 half, 1 half, and 1. So you're taking B over A, so 1 half times 2/3 because you're dividing. So 2's would cancel and you get 1/3. Here you're taking 1 half times 2 over 1. So that 2's are going to cancel and you're going to get 1. And here you're going to take 1 over 2. So the smallest of those looks like it's 1/3. So I would be using row 1. So I'm going to use row 1 and column 2. So keeping this in here, we don't have to write that down. Just hit enter, enter. And we're going to do, based on our test ratio of A over B, we're going to do row 1 and column 2. Notice looking at the bottom, we don't have any negatives left. So it looks like we've got an optimal solution. So let's write down what we've got. So 0, 1, 0, 0. 1, 0, 0, 0. 2/3, negative 1/3, negative 4/3, and 20. We've got negative 1/3, 2/3, negative 1/3, and 20. We've got 2 unit columns there, 0, 0, 1, 0, and 0, 0, 0, 1. Finally, 1/3, 1/3, 1/3, and 40. let's write down what we've got as our solution here. So we actually have two problems we can read solutions for. So obtain the solutions to the minimization problem. So that was the original problem. So remember what's showing here is the dual, right? So for the dual, we have a U here is active and V is active, and it looks like the slack variable Z is active, okay? Now remember what we did to get this tableau, right? To get the dual problem. So we took the transpose of the original problem. So normally when we read one of these, we read the solutions across. Well, but we took the transpose, and the reason it's nice to call those slack variables X, Y, and Z is because their solutions actually just read down. So we have to read down because we took the transpose if we want the solution to the original problem before we did the transpose. We read down. Here's what we've got. X is equal to 20. Y is equal to 20. And Z is equal to 0. So 20, 20, and 0. And we can also find the solution to the standard maximum LPP if we wanted to. When we would still read across as usual, we'd have U is equal to 1/3 and V is equal to 1/3. So that would be a 1/3 and a 1/3. But note that the optimal value for both would be the same. So for each, C is equal to P is equal to 40. Trust me, the more of these you do, the easier it gets. The process becomes more natural. But it's always important to determine which type of LPP you're starting with, whether it's a standard max, whether it's a minimum with less than or equal to constraints, or if it's a standard min when we have to use duality. So here we've got C equals, it's to minimize, they're all greater than or equal to, and it satisfies the non-negative objective function condition. So this is going to be a dual problem. So we have to come up with the dual problem, which means we want to maximize P, right? Now, it might help to go ahead and jot down the matrices. So let's do this matrix first, and then we'll come up with the dual problem. So we've got X and Y, so 4, 1, remember we don't do anything with slack variables yet, so 100, and then 2, 1, 80, and then 1, 3, 150, and remember that objective function at the bottom, 1, 2, and if you don't want to put anything in there, you don't have to, but you can also put a 0. So we take the transpose of that. So the rows become the columns, so 4, 1, 100, 2, 180, 1, 3, 150, and 1, 2, 0. And we come up with our dual problem. So this reads off as 4U plus 2V plus 1W is less than or equal to 1. 1U plus 1V plus 3W is less than or equal to 2. And then our objective function is P equals 100 plus 80V plus 150W. So let's write those down. So P equals 100U plus 80V, and we'll use W as our other variable. Subject to the constraints that 4U plus 2V plus W is less than or equal to 1. Subject to 1U plus 1V plus 3W is less than or equal to 2. And this is where we turn, now this is the dual standard max. Notice we're maximizing. We've got all less than or equal to. We can't forget, and I may have forgotten this on the other problem, go back and double check me. All of the variables have to be non-negative. That means my system of equations using slack variables would be 4U plus 2V plus W, and then we're going to use X and Y as our slack variables. So take up the slack for the less than by adding some slack to it and getting equal to 1. Take up the slack by adding y as a slack variable and getting that up to 2. And then we've got our objective function. Remember, you always have to get the terms to the same side as p. So minus 100u minus 80v minus 150w plus p is equal to 0. I've tried to help us out by going ahead and putting these tableaus in here and labeling everything. So we've got u, v, w, and then slack variables of x, y, and actually I've got an extra variable in here. So I accidentally didn't delete that from the previous problem I copy and pasted from. So let's just mark out z. We don't need z. We would only need z if we had a third equation right here. 4u, reading off here, plus 2v plus 1w. We do have a slack variable of x, no y, no p, and a 1. Reading off here, we have a 1u, we've got a 1v, we've got a 3w, nothing for x, we've got a slack variable of y, nothing for p, and that's equal to 2. And then for p, if you want to put these diagonal so you're not squished in there, you can. Negative 100, negative 80, negative 150, and then 0, 0, 1, and 0. Again, looking for the most negative, looks like minus 150, so we're looking at column 3, and then we look at our test ratios. So A over B, this is A over B. So this is A, and this is B, so we're doing A over B. 1 over 1 is equal to 1. 2 over 3 is smaller than 1, so it looks like that needs to be my pivot. So I'm going to do row 2 and column 3. Got a smaller matrix this time. We've got 3 rows, 7 columns still. So 4, double check your entries, look at your columns. And quit. Call it Pipita, hit enter, enter again, and we're on row 2, column 3. Alright, we got some negatives still, so we're going to do our little shortcut method here. The most negative looks like it's in column 1. So let's write down column 1. We've got 11/3 and 1/3. And let's look over at the constant column to get our ratios. We've got 1/3 and 2/3. So we've got A over B, so that's multiplying by the reciprocal, so that's 1/11. And then here we've got A over B, so 2/3 times the reciprocal, which would be 2. And definitely 1 over 11 is smaller. So it looks like we're row 1, column 1. So row 1, column 1. Hit enter, enter. And we're going to do row 1 and column 1. Still leaving me with a negative value here. We've got one more notation to make here. We've got column 2, I believe. Column 2, we've got 5/11 and 2/11, and let's get our constants. (1 over 11) and 7 over 11. So taking 1 over 11 divided by this one, so multiplying by its reciprocal, that would be 1/5. And taking 7 over 11 times its reciprocal, 11 over 2, well, that's 3.5, so that's definitely bigger. So we're back at row 1. So column 2 and row 1. So enter, enter, row 1 and column 2. That cleared out all of our negatives. Let's write down our final tableau. Got 11/5 and negative 2/5 and 16. Got a unit column. We've got a unit column and 3/5, negative 1/5, and 18, negative 1/5, 2/5 and 44, 001, 1/5, 3/5, and 106. So let's erase some of our scratch work here. So let's look at our primal solution. So this goes to the minimum problem. Remember, if we want the primal solution, we're not looking for u and v, we're looking for the original variables x and y, and we read those down because we did the transpose up here. So we've got the minimum value as being 106, and that's going to occur. Let's look at our variables reading down. X is equal to 18, and y is equal to 44. So as an ordered pair, that would be 18, 44. We could also get the solution to the dual problem if we wanted to. We would have v is equal to 1/5. We'd have w is equal to 3/5. And then, of course, u is not listed, so u would equal 0. And p would equal 106 as well. But it just asked us for the primal problem. You may want to try to pause the video just to see if you can do this next one on your own, just to get kind of used to the process on your own. I know lots of times when you're watching people do something, it makes complete sense, and then when you get on your own, it's like, oh no, I don't know how to do this. So it's one reason I chose to flip this course in particular, because it's all about processes, and you have to know how to do those processes on your own. But I'll go ahead and get started with this next one. We do have a standard minimum that has the non-negative objective function constraint satisfied. We have a dual solution here. We can write the dual problem. In order to get that, we've got to think about the transpose of the basic matrix. Here we've got 1, 1, 1, and then 20, and then 3, 1, 0, and 14, and then 1, 2, 3, 25, and then our objective function at the bottom, 3, 1, 2, and you can leave it blank or put a 0. We need the transpose of that, and that's going to give us the dual problem. So the rows become the columns, vice versa, so 1, 1, 1, 20, 3, 1, 0, 14, 1, 2, 3, 25, and finally at the end 3, 1, 2, 0. This corresponds to the standard maximum with, so we would maximize P equal to 20U plus 14V plus 25W. And we would have constraints of U plus 3V plus W is less than or equal to 3 because we're going to standard maximum. And then U plus V plus 2W is less than or equal to 1. And then U plus, we're not going to have the V because of 0, we're just going to have a 3W. And it's going to be less than or equal to 2. And don't forget the non-negative variables. The U has to be non-negative, V has to be non-negative, and W has to be non-negative. We can turn that into a system of equations by adding slack variables. We're going to add to this first equation an x as a slack variable, and to the second equation we're going to add a y as a slack variable. And this time we do need a z because we've got a third equation. So we'll have u plus 3v plus w plus x is equal to 3. And then this one will give me u plus v plus 2w plus y is equal to 1. So we're treating x and y as slack variables, taking up the slack from the less than to turn it into equal to when we add more to it. And finally, u plus 3w plus, we're going to use z for the third slack variable, and now that's no longer less than, that's going to equal to. And for our objective function, we have to move all of these terms on the same side as p. So I'll put that down here. Negative 20u minus 14v minus 25w plus p equals 0. So you've got your new system of equations for the dual problem. So we're going to write down those coefficients. So 1, 3, 1. Notice I've got x, y, z for my slack variables. So 1, 3, 1. X is the slack variable in the first equation. Don't have y or z or p, but I have a constant of 3. I've got 1, 1, 2. I don't have an x, but I do have a y, so 0 for x, 1 for y. No z, no p, but I do have a 1 constant. And then I've got a u, I've got a w, so no v right here. I've got a 3 for a w. Don't have an x, don't have a y, but I do have a z for a slack variable, and the constant is 2. And now I have to put the objective function down here. So negative 20, negative 14, negative 25, 0, 0, 0, 1, 0. Most negative, negative 25, puts me in this column, so then I do my test ratios. 3 over 1 is 3, so A over B. 1 over 2, and 2 over 3. Well, 2/3 is 0.6 repeating, and that's a lot bigger than 0.5, so I need to use this one as my pivot. So we got 4 by 8. Check your columns. Whenever you're ready, go ahead and call up your pivot program. And it looks like we're on row 2 and column 3. And we've got some negatives at the bottom, so let's do our little shortcut of making some notes to see what our pivots are so we don't have to write down all those tableaus. So it looks like columns 1 and 2. Alright, so column 1, here's our options. We've got, oh wait, which one's the most negative? We'll see negative 1.5 and negative 7.5. It's going to be column 1. So column 1, we've got 1/2, 1/2, and negative 1/2. Remember, you can't pivot on a negative, so it's not going to be row 3. So let's go to the end and look at the constants for row 1 and 2. So this is 5/2 and this is 1/2. So doing the, remember this is A over B. Test ratio, we'll have 5/2. Multiplying by the reciprocal when we divide is going to be 5. And 1/2 is going to be 1. So it looks like we need row 2. So column 1 and row 2. So enter, enter, row 2, column 1. And I do believe that got rid of all of our negatives. So that was a quick one. Alright, so let's write down we've got 0, 1, 0, 0, there's a unit column. 2, 1, negative 1, 6, negative 1, 2, 1, and 15, another unit column. So remember, this is the dual solution, so we can read down to get the primal solution, which is what it's asking us for here. So we've got x is equal to 0. We've got y is equal to 20. And we've got z is equal to 0. And it looks like our optimal value of minimum of c is 20. So if we wanted the dual solution, just to make a note here, so this is the primal solution, we would also have a maximum of p of being the same thing, so the optimal values will be equal. but the solutions will be different because they're different variables. So this one, let's see, we've got a unit column there, so 1 corresponds to u. We've got a unit column here, so that's a slack variable for the dual problem. We've got a unit column here, that's a slack variable for the dual, and we've got that. So it looks like u for the dual, u would be 1, and then since v and w are not active, they would both be 0, and we would have that solution.